Okay, this is the first lab in chapter 4. It's called Dissolving a Solid in Water. It is on page 72 of your textbook. What I would like you to do while you're watching the video is have your book out as well, because a big part of the learning comes from the blue dot questions. So as I'm showing you how to do the lab, I'm going to be talking about the blue dots, so I'd like you to have them in front of you so you can see them. Basically, if you read the first paragraph, it's talking about dissolving solids into liquids. So it's talking about qualitative observations. The end of the first paragraph says, "Are you sure that not even a tiny amount of chalk or sand dissolves in a gallon of water?" And then a follow-up question is, "Can you dissolve as much salt or sugar as you wish in a glass of water?" So we're not doing either of those because we're not using salt or sugar or sand or chalk. But they do pose some interesting questions about how substances dissolve into liquids. So really what we're exploring here is the nature of a solution and kind of what happens. So what we're going to do is we're going to start off with a test tube with 5 cubic centimeters of water in one, and then a second test tube with 20 cubic centimeters of water. Obviously a significantly larger amount of water in the second test tube. So our solute, what we're going to do is we're going to take a solid and we're going to put it into the liquid and let it dissolve. The first, I guess, new vocabulary term that's being presented in this chapter is the word solution. So a solution is basically any time a substance dissolves into another substance. Okay. In this case, we have water. Water is our solvent. That's another vocabulary word that we're going to be getting into in the next section. The solvent is usually the liquid that's being dissolved into. What we're going to use for our solid in this case is this stuff called copper acetate. I like to refer to it as blue stuff just because the nature of the substance doesn't really matter. So calling it blue stuff will be sufficient for what we've got to do. So if you read through the lab, the first thing that they want us to do is to add 0.15 grams of the blue stuff to each of the test tubes. So we're going to measure out 0.15 grams, and we're going to add it to each of the test tubes, and then we're going to shake it up and kind of see what happens. See if it dissolves, that sort of thing. And if you kind of look ahead to some of the blue dot questions, you'll get an idea of what we're going to be looking for. Okay, so I've got 0.15. Perfect. Okay, so now in each of these two massing dishes, I have 0.15 grams of blue stuff. So I'm going to add 0.15 to the 5 cubic centimeters of water. I'm going to stop run and I'm going to shake it. And I'm also going to add the exact same amount of solid to 20 cubic centimeters of water. So both test tubes have the same mass of blue stuff. So now what we're going to do is give it a minute or two to dissolve and see what happens. We'll compare them and answer a few questions about the solutions that we've created. It is interesting to note these solutions actually get cold when you mix them. The implication there is that this is an endothermic reaction, which is the opposite of exothermic. Exothermic is a reaction where it gives off a lot of heat and it gets hot. The opposite of that is when it gets cold during a reaction, which would be endothermic. So whatever this substance is, when it is mixed with water, there's some kind of endothermic reaction going on because it gets colder. So that's an interesting thing to note. Okay, almost there. Okie dokie. The first blue dot question, if you look in your book, says, "Did all of the solid dissolve in both test tubes?" So the first thing we want to do is make sure we shake it long enough. We're almost there. We want to make sure it's shaken long enough to give it every opportunity to dissolve if it's going to. After a little while, if it doesn't dissolve, then, if we've mixed it long enough, we can feel confident that we gave it its best shot. But if you don't mix it long enough, then you're not really sure if it's because of the mixing or if it's because of the solid. So we want to give it enough chance to dissolve. Let's see. Okay, this looks good. All right, so let's see if we can get a good background here. You can tell, first of all, that the colors are different. And I guess we'll get to that in a second. The first thing, let's see if you can tell on the video. I don't know if you can see it or not, but all of the blue stuff is dissolved. And in the 20 cubic centimeter solution, it's all dissolved as well. There's none left in there undissolved. So the first blue dot question says, did it all dissolve? So yes, the solid does dissolve in both test tubes. It dissolves completely. I wonder if I put this back here. You can see it a little bit better. Oh yeah, that's good. Okay. The second question says, and this is a really important one. So if you're watching this, if you're taking some notes, this is one that we definitely want to pay attention to. So we're going to come back to this quite a bit. It says, do you think that each cubic centimeter of solution in one test tube, okay, so one or the other, contains the same amount of dissolved material? So let me rephrase that question for you because it seems a little bit, it's tricky. First of all, what it's asking us to do is just to look at one test tube, not both of them. We're not comparing them to each other at this point. We're just looking at one test tube. If I were to take 1 cubic centimeter of this solution right here and pour it into a little dish, and then take another cubic centimeter and pour it into another dish, and if I were to compare those two samples of this solution to each other, the question then says, do you expect it to have the same amount of dissolved material? Well, the answer is yes, it should. If I pour, let's just say I pour half into one and half into other, that might make it even easier. If I took this solution and I pour half of it into one dish and half into another dish, I would expect both of those portions to have the same amount of dissolved material. It's kind of like if you think about iced tea, for example. If you make like the powdered kind of iced tea, and you take water and you put the powdery mix in there and you mix it up and you mix it up, as long as you mix it up really well, no matter how many glasses of iced tea I pour from that pitcher, they should all taste the same because they should all have the same amount of like iced tea mix dissolved in that glass. The idea is it dissolves uniformly. The word uniform means it dissolves the same throughout the entire solution, which is, you know, part of it's like, well, yeah, of course it does, because we observe this in our everyday life. We just don't actually call attention to it. But it should dissolve evenly throughout the entire solution. It would actually seem very odd for maybe the top half to have more than the bottom half, because why would that happen? Well, the answer is it doesn't happen. So we would expect it to dissolve evenly throughout the entire solution. Somebody's trying to get my arm. Okay, so that's what that question is saying. Do you think that each cubic centimeter in one test tube contains the same amount of dissolved material? The answer is yes. It should include the same amount of dissolved material no matter which portion of this test tube I look at. Now, same thing here. Every portion of this test tube also, compared to itself, should have the same amount of dissolved material. So if I divide this one up in half, or if I divide it in fourths, or if I divide it in quarters, or whatever, fourths is quarters, I guess, eighths, whatever, every portion of this should have the same amount of dissolved material in it. And we call that word uniform. Does it dissolve uniformly throughout the solution? Yes, it does absolutely dissolve uniformly. So every cubic centimeter has the same amount of dissolved solution or dissolved solid as every other cubic centimeter. That's obviously an important one because I spent a lot of time on it. So we'll come back to that throughout the whole chapter, actually. All right, the third blue dot says both tubes contain the same amount of dissolved material. What that means is I put 0.15 grams of blue stuff here and the same amount of blue stuff here. But the question goes on to say, is the shade of the color the same? Well, you can tell pretty clearly that this one is darker than this one, which again seems logical, whether you know how to explain it or not. I mean, we would expect this one to be darker. The reason is this one has less water, so there's less substance for the blue stuff to dissolve into. So it doesn't spread out nearly as much, so it's going to be darker. We call that being more concentrated. This one is more dilute. Dilute means it spreads out throughout a much greater amount of liquid. So the blue particles have a lot more room to spread out, so the color is going to be lighter in shade. Okay, the next part is for us to add another 0.15 grams to each of the test tubes. So let's measure out some blue stuff and see what happens. Again, we're adding the same amount for both of the test tubes. So now we're going to be up to a total of 0.3 grams. So I already added 0.15, and I'm going to add 0.15 again for a second time. Alrighty, so I have 0.15 grams in each of the massing dishes. So let's add another 0.15 for a total of 0.3. And to this one, another 0.15, which gives us a total of 0.3 in this test tube as well. Okay, now the fun part. We get to shake. Try to keep it on camera. Shake, shake, shake. Sometimes it gets stuck to the side of the test tube though. This is the tedious part. Sometimes that happens though in a lab. You have to be patient for our results to turn out correct and accurate and precise and all that good stuff. You can definitely tell these are cold. Oops. Don't want to spill any of our solution. Almost there. Almost there. You don't want to turn it sideways or shake it too vigorously because this one's already leaking a little bit. I got some blue stuff in my hands. So it makes the dissolving process a little bit tricky because I can't really shake it as thoroughly as I would like to, so it's going to take a little bit longer. Almost. So we're leaking all over the place. There we go, let's get that out of there. Okay. Let's see. I don't know how well this is going to be able to show up on here, but hopefully you can see that in both of these test tubes, there's no stuff left undissolved. All of it is completely dissolved in both test tubes. And again, you can definitely see a difference in their color, which makes sense because the one with less water, again, has less room for all that blue stuff to spread out. The one with more water has more room for all the blue stuff to spread out. So it's going to make sense for the solution with 5 cubic centimeters to be darker in color. And you can probably see it a little bit better there. Alright, so let's look at the second set of Blue Dot questions. It says, did the 0.3 grams of blue solid dissolve as well in 20 cubic centimeters as in 5 cubic centimeters? Well, yeah, it dissolved equally as well in both test tubes. That's not saying they're the same color. That's not the same thing. What they're saying is, did it dissolve as good in here as it did in here, or as good in here as it did in here? Basically, both test tubes completely dissolved all the blue solid the second time as well. And so yes, it dissolved equally as well in both test tubes. The next Blue Dot says, is the color uniform throughout the solution? Yes, we spent a lot of time the first go around talking about uniformity, but yes, it's definitely uniform. You can see the color is the same all the way throughout when you're comparing it to itself, and the same thing here. The color is the same all the way throughout. What that means is it's uniform. Uniform means the same throughout. Okay, so yes, the colors are uniform in each test tube. However, this next blue dot asks you to, now we're going to compare them to each other. Is the shade of color the same in the first and second solutions? Well, no, obviously they're not the same. This one is much darker. Oops, that's the light one. This one's much darker than this one is. Again, because this has less liquid for all that blue stuff to dissolve into. This one has more room to spread out, so it's going to be a little bit lighter. Okay, and for a third and final time, we are going to add some more blue stuff. Now, while I'm doing this, it might be worth talking about some of our definitions. I think I mentioned earlier that this is a very vocabulary intensive chapter. Lots of new vocabulary. So it's probably worth noting, I think I already mentioned, well, the first part I did, what we're doing is creating solutions. Obviously the word solution can have many meanings. In math, you think of a solution as an answer to a math problem. Also in life, sometimes we look for solutions to our problems. That's not what solution means in this case. In this case, in science, a solution is when you dissolve any substance into another substance. So we're looking at that today. We're dissolving blue solid into water, and we're going to compare them. So solution is one of our vocabulary words. Two more that are really important here. The solid material, or the substance that's doing the dissolving, like the blue stuff gets dissolved, we call this the solute. So the stuff that dissolves into the liquid, we call the solute. So in this case, our blue stuff is the solute, and then the liquid that it's being dissolved into is called the solvent. So the solvent in this case is water. The solute is blue stuff, which again, more technically, is called copper acetate. So far we have the words solution, solvent, and solute that are new. And don't you worry, there's going to be a lot more where that came from. There's lots and lots and lots of vocabulary in this chapter. So in this chapter, maybe even more so than in some of the others, we're going to have to make sure we spend some time understanding the terminology, because that is half the battle. So if you don't know what the words are referring to or what the words mean, it's going to make it a lot more difficult to answer questions about it. Okay, so let's give this a few minutes. Shake, shake, shake. Again, the tedious part. The good news is, after this one, we are about done with the lab. We'll finish up our blue dots. I'm going to shake it really well without spilling it, she says as she spills it. Of the test tube here. Almost. Okay. Alrighty. Now, what we should notice at this point, and I have no idea if the camera is going to pick this up. I hope it does. This solution, as with the last two times, is completely dissolved. All the blue stuff completely dissolved into the 20 cubic centimeters of water. This is the part I'm not sure if you're going to be able to see. Oh, good. You can kind of see that. What you should notice at the bottom of this test tube is that there's blue solid that is left undissolved. Now, I can tell you, and you might want to take my word for it just because of timing, no matter how long I shake this, I could shake it for the next hour and a half, that blue stuff that's left in the bottom, I'll let it settle out again, so you can see it on that side. There it is. That dark spot in the bottom of the test tube, that's blue solid that is left undissolved. And my point that I was about to make is that no matter how long I shake this, it's not going to dissolve. That 5 cubic centimeters of water will not dissolve any more blue stuff. We call this a saturated solution. So again, there's another vocabulary term that you definitely need to know. A saturated solution is a solution in which no more solid, or I should say substance, will dissolve. Now, the only physical evidence that I have that this is a saturated solution is that I can physically see that there is blue solid left in the bottom of the test tube that will not dissolve. So, in terms of being able to prove a substance, in order to be able to prove that a solution is saturated, you have to be able to see that there is stuff left that will not dissolve. There it is. I keep shaking it so it moves. There it is again. Right there. So again, you have to be able to physically see that there's leftover substance that will not dissolve. That is how you absolutely know it's saturated. There's no other way for us to be able to tell if it's saturated other than by having to be able to see it physically. If you can't see it, then you're not going to be able to say one way or the other if it's saturated. So by being able to see leftover solid in the bottom that will not dissolve, that's how you know it's a saturated solution. So again, if we look, well, let's do this first. Let's go over the last few blue dots, because at the top of the next page on 73, it gives us the definition of saturated solution. So, third to last blue dot, it says, what is the total mass of the blue solid now in each test tube? Well, we added 0.15 3 separate times, so now we have a total of 0.45 grams in each of the test tubes. It then says, what do you observe? The observation at this point is that the 20 cubic centimeter solution dissolves entirely. The 5 cubic centimeter solution has blue stuff left undissolved at the bottom. And then the last blue dot is asking us to do a little bit of, it's actually a little bit of math, so let me give you my 2 cents on this. It says, how many grams of blue solid do you think would have to be added to 20 cubic centimeters of water before the solid stops dissolving? So here's, I'll show you my little picture. Here's 5 cubic centimeters of water, and then here's 20 cubic centimeters. Okay, so we have 5 cubic centimeters. I don't see that. If I get closer. Oh, there it is. Well, that's a little bit weird. All right, well, if I've got a 20 cubic centimeter solution and a 5 cubic centimeter solution, in this test tube over here, I don't really know the point at which it stops dissolving. I do know, let's see if you can see this. Oh boy. Turn it this way. Light adjust. Oh gosh, okay, I think we're almost there. It's a little fuzzy, but you get the idea. Okay, if you look at the one on the left, it says 0.30 to 0.45. The point I'm making here is that when I put in 0.3 grams total in the 5 cubic centimeter side, all of it dissolved. However, when I added another 0.15, some of it was left undissolved. So I don't really know the exact amount that has to be added to where it's saturated. I just know it's somewhere between 0.3 and 0.45. Now, this is a 5 cubic centimeter solution. The 20 cubic centimeter solution is 4 times the amount of liquid. So logically, it would take 4 times the amount of solid to get to the saturation point, the point where no more will dissolve. So if we do our math, it would be somewhere between 1.2 grams and 1.8 grams. So mathematically, because that solution is 4 times more so than the 5, that's really hard to see. But you get the idea. It should take 4 times the amount of solid because it's 4 times the amount of liquid to get to the point where no more will dissolve. Okay, last part. The only sentence at the top of 73, it says, a solution in which no more solid can be dissolved is called a saturated solution. So this is a saturated solution, the 5 cubic centimeter one. This one is not. The physical evidence that we have is that there is solid that is left undissolved. That's how I know that no more will dissolve. When I can physically see that no more will dissolve, that's how I know it's saturated. This one, everything's dissolved. So I'd have to keep adding more and more and more to get to the point where no more dissolves. And we determined that's probably somewhere between 1.2 grams and 1.8 grams. So the last blue dot says, do you have a saturated solution in either test tube? Yes, the 5 cubic centimeter solution. What is your evidence? The evidence is that I can see blue solid left undissolved in the bottom of the test tube. So that is lab 1.4. For my students, I will be doing a pen cast as well. So if you have any questions, just let me know.